Now we're going to look at the electric field of a curved wire at the point that is at its center of curvature. This actually should be a little bit easier since there's a little bit more symmetry and less variables. So from point P to the wire is going to be the radius of curvature. So that's going to be constant at every single point. So if we look at a small section of the wire, that little chunk of charge there is going to be a distance r away from point P, and that's going to contribute a small amount of field in that direction. If we look on the other side, try to keep it symmetrical, that little packet of charge there is going to contribute field in that direction. So we can see with the symmetry of the shape that the y components of those are going to cancel each other out. So we only are worried about the x components of each of these fields. And the angle we're going to worry about from there to there. And if we go from the edge of the wire to the axis, this is going to be the total range that we're going to integrate between. So we're going to be going from really positive theta to negative theta in our integral. So let's set up our equation here. Every small amount of field is coming from those small amounts of charge, and the nice thing is that r on the bottom is the radius of curvature, and it's constant. And we're only worried about those x components again, so we're going to multiply this by the cosine of that angle theta. Alright, so now let's look at what we're going to have to substitute in. This total charge Q is over the entire length of that wire, and that is its linear charge density. That means for that little packet of charge dq, the density of charge over dq per that small amount of length has to be the same. Call that ds because it's an arc length. And to find arc length, it's going to be the radius times the angle, and that's just a really, really small portion of the angle there. We're going to manipulate that because we want to get the dq out of there. We're going to put dq in terms of the density, radius, and the variable theta. And I think that's the only substitution we're going to have to make here. So if we add up all the little DEs, we're going to get the total electric field. K is a constant. R is a constant. Now we're just left with dq cosine theta, but dq is lambda r d theta cosine theta there. So we only integrate the cosine of theta d theta. Lambda is constant, r is constant. Actually, that one r cancels out one of those r's over there. So the integral of the cosine of theta d theta is the sine of theta. And we're going to evaluate this between the thetas. Forgot to bring that r down. And we can do this little trick where the total angle is twice the original theta, so we can actually change the parameters to 0 to theta and multiply the entire thing by 2. But if you think through it, if I plug in theta into theta, which is weird, but you'll get the sine of theta minus the sine of negative theta, which is basically adding 2 sines of thetas together. So we'll get 2 times that sine of theta.